This is a multiple-choice question testing your understanding of quadratic discriminant analysis, QDA, a classification algorithm in machine learning. Here's the core problem. I'm using QDA, a specific type of classifier, to sort data into two groups based on two characteristics. The data's not easily separable by a straight line. I need a more complex method. I'm setting up a scenario to test your knowledge of QDA. I will use this to illustrate a problem that QDA is particularly well suited to solve. Specifically, the scenario uses scikit-learn's QDA implementation and focuses on non-linearly separable data. Statement A says QDA is a good fit because it assumes that each data group follows a bell curve, Gaussian distribution, with potentially different spread patterns, covariance matrices. This is accurate, because QDA handles such situations very well. Statement B claims that QDA likely does better than LDA because QDA handles curved separation boundaries. I agree. LDA assumes linear, straight-line boundaries which may not work well for nonlinear data like this. Statement C warns that QDA is quite sensitive to outliers. This makes sense. If I have some data points that are far from the norm, QDA's calculation of the Gaussian distribution spread will be greatly affected. Statement D suggests QDA needs more data than LDA to achieve similar accuracy. I agree. QDA estimates more parameters, those different covariance matrices. More parameters need more data for reliable estimation. I see how sensitive QDA is to outliers. Because QDA calculates separate statistics for each class, a few unusual data points can really skew those calculations. Think of it like this. If you're figuring out the average height of two basketball teams, and one team has a few unusually tall players, that average will be way off, influencing how you classify players overall. This affects QDA's accuracy. Since QDA calculates more things than LDA, it handles different statistical shapes for each class. I need more data points to get reliable results. You need enough data to accurately represent the spread and shape of data in each class. Let's compare QDA to LDA, linear discriminant analysis. LDA assumes that all classes have the same statistical shape, making the calculations simpler. This means LDA needs less data and is less susceptible to outliers. LDA makes a simplifying assumption. It assumes that the spread and shape of the data for each class are the same. Covariance matrices are a way of representing this spread and shape. This is different from QDA, which allows for different shapes in each class. LDA creates a straight line, or a hyperplane in more than 2 dimensions, to separate classes. Think of it as drawing a single, best-fit line through data points. This means it can only deal with linearly separable data. Because LDA makes the simplifying assumption of equal statistical shape for all classes, it is less affected by individual unusual data points, unlike QDA. Think of this as being more robust to single large or small data points. I assume that the data for each class follows a bell curve, or Gaussian distribution. This is a key assumption of quadratic discriminant analysis, QDA. Unlike linear discriminant analysis, LDA, I allow each class to have its own unique spread or scatter, represented by a covariance matrix. This is what lets QDA handle nonlinear relationships. Because each class can have its own shape, I can create curvy decision boundaries, not just straight lines. This is crucial when dealing with data where classes aren't cleanly separated by a straight line. Because I estimate separate parameters for each class, including their spread, covariance, outliers can disproportionately influence these estimates, and thus, my overall accuracy. I need more data to reliably estimate all the separate parameters I use, separate covariance matrices for each class, compared to LDA, which makes fewer assumptions about the data. These are the key features that define how I work, and how I differ from other methods like LDA. I'm working with a dataset that has 2 characteristics to describe each data point. The data points belong to one of 2 groups, and these groups are not easily separated by a simple line. They're intertwined in a more complex way. This statement is true. That's precisely what QDA does. I fit a Gaussian distribution to each class, allowing for different spreads for each. This is true. Because I can handle nonlinear boundaries, I am generally expected to perform better than LDA, which assumes linear separability, when dealing with curved class boundaries. This statement is true. Outliers can greatly affect the estimation of the class covariance matrices, which are critical to my performance. This is true. Since I estimate more parameters, I need more data for reliable results than LDA, which has fewer parameters. This problem focuses on understanding how quadratic discriminant analysis, QDA, works, especially when we compare it to a similar method, linear discriminant analysis, LDA. I'll explain the key differences and how that impacts which method you choose for different datasets. We'll look at a scenario with two features and two classes of data, so we can visualize the types of problems QDA solves best. Here's the core question. Given a dataset where the two classes of data are clearly not linearly separable, meaning you can't draw a single straight line to perfectly split them, what are the true statements about using QDA for classification? We need to understand what makes QDA tick and how it differs from LDA to answer this. Because we have a non-linearly separable dataset, one that cannot be perfectly divided using a single straight line, LDA, which assumes linear separability, will likely struggle to classify the data effectively. QDA, however, is more flexible. It can model curved class boundaries because it allows for different covariance matrices for each class. This means I expect QDA to outperform LDA here. Because QDA estimates separate covariance matrices for each class, outliers can significantly skew these estimates. Imagine an outlier point in one class. It will strongly influence the estimated covariance matrix for that class. Therefore, this makes the model less accurate and more sensitive to the noise introduced by outliers. This is a major drawback of QDA. QDA's core strength is that it models the data for each class as a Gaussian, normal, distribution. But crucially, each class has its own covariance matrix. This is a crucial point. It's what allows QDA to handle nonlinear decision boundaries effectively. That's why, when faced with the non-linearly separable data in our scenario, QDA is a suitable choice. Since QDA estimates more parameters, separate covariance matrices for each class, it generally needs a larger dataset for reliable estimation. Think of it like this. With more parameters, you need more data points to constrain the model sufficiently and avoid overfitting to the training data. So, yes, QDA is more data hungry than LDA. I'm analyzing statements about quadratic discriminant analysis, QDA, and its performance on data that cannot be perfectly separated by a straight line. This means we have a situation where QDA's ability to model curved decision boundaries is important. Statement A is true. QDA assumes that data points within each class follow a normal, Gaussian, distribution, and importantly, it allows these distributions to have different shapes and orientations, represented by different covariance matrices. Statement B is true. Because the data is non-linearly separable, meaning it cannot be easily split by a straight line, QDA, which can handle curved decision boundaries because of its separate covariance matrices per class, will likely outperform LDA, linear discriminant analysis, which is limited to linear boundaries. Statement C is true. Outliers can significantly skew the calculations of the covariance matrices in QDA since they strongly influence the shape of the estimated distributions. This makes QDA's results vulnerable to these extreme data points. Statement D is true. Because QDA estimates many more parameters, separate covariance matrices for each class, it needs more data to reliably estimate these parameters and avoid overfitting, compared to LDA, which makes fewer assumptions and therefore requires less data. This describes the core assumption of QDA. Data within each class is drawn from a Gaussian, normal, distribution, but these distributions can have unique shapes and orientations. For each class, represented by the covariance matrices, a nonlinear decision boundary is a curved line, or higher dimensional surface, that separates data points of different classes. It is in contrast to a linear decision boundary, which is a straight line. QDA's capacity to model different covariances enables it to create these curved boundaries. I see that you're asking about the Gaussian distribution assumption in QDA. Remember, QDA assumes that your data points for each class are scattered like a bell curve, a Gaussian distribution. But what makes QDA special is that it allows each class's bell curve to have a different shape and spread. This is captured by the covariance matrices, which describe how the features are related within each class. So, unlike LDA, which uses a single shape for all classes, QDA can use multiple shapes, allowing it to capture nonlinear relationships between features. Isn't that cool? This is the core problem. We are given a classification problem using QDA. The algorithm has two features, implying two-dimensional data. There are two classes with data that can't be easily split by a straight line, linearly separable. Instead, a curve is needed, non-linearly separable. The nonlinear decision boundary. Because QDA can model different covariance matrices for each class, it can create a curved line separating the classes. This is in contrast to LDA, which is limited to creating only straight line boundaries. Let's recap quadratic discriminant analysis, QDA. It's a classification technique that assumes each class's data follows a Gaussian distribution, bell curve. The key is that QDA allows each class to have its own unique shape and spread. This lets it handle situations where classes aren't linearly separable. The classes are not easily separated by a straight line. Statement A is true because, as we've discussed, QDA does exactly that. Each class gets its own Gaussian distribution, characterized by its own covariance matrix. This allows for flexible modeling of class shapes. Statement B is true due to the nonlinear boundary feature of QDA. Because the data is not linearly separable, a curve, not a straight line, is needed to separate the classes. QDA's ability to model these curved boundaries leads to better performance than LDA, which can only create straight line boundaries. Statement C is true. Since QDA estimates separate covariance matrices for each class and outliers can influence the shape of these distributions, the model becomes sensitive to outliers. Even a few outliers can significantly skew those calculations. Statement D is also true. QDA estimates more parameters than LDA, because it models a separate covariance matrix for each class, which requires a more significant amount of training data to accurately estimate those parameters. Otherwise, you risk overfitting the data. This is simply the full name of the classification algorithm we are discussing throughout this question. QDA is a powerful algorithm for classification problems, especially those with nonlinear relationships. Its main strength lies in its ability to capture complex class distributions which LDA cannot.